Hello student, in this video I am going to discuss about how we can fill any polygon or any object having edge boundary. We need to fill that object with some color, with our desired color. So how we can do that in computer graphics to display any object having edge boundary. So fill any polygon, we might fill that using some solid color, or we might fill that using some pattern color, and that pattern can be defined using different functions, or as per your algorithm you can fill it up, and that pattern might be arbitrary also. So to represent the polygon, we can see here, uh, you can see here P equal to, suppose P is the polygon, then this is the first vertex, second vertex. In this way all the vertex of the edges will be included inside that set, and this set width will be said as polygon. So in this way we can represent the polygon. The polygon can be displayed by drawing a line between, here you can see if we draw a line from x1 to a y x2, next suppose there is another line x2 y2 to x3 y3, and in that way till xn to yn, or there might be any cross connection between any other points also. So until the n vertex, in order to close up the polygon, a line between xn and yn and x1 and yn must be drawn. So to close up the polygon we need to end the drawing by connecting x and yn and x1 y1. So one problem with this representation is that if we wish to translate the polygon, it is necessary to apply transformation to each vertex in order to obtain the translated polygon. Means suppose we need to move, or we need to translate that polygon from one point to another point in the monitor, in the display system, then every point of the polygon need to be translated. So that is the problem with this representation. But still, for objects described by many polygons with many vertices, this can be a time consuming process. So now one method for reducing the computational time is to represent the polygon by absolute location of its first vertex and represent subsequent vertices as relative position from the previous vertex. This enables us to translate the polygon simply by changing the coordinate of the first vertex. So to reduce the problem of time consuming in the previous representation, we can do what? We can only put this first vertex as absolute location in the Cartesian geometry as the reference for the monitor, which should be the absolute location, and then all other vertices would be at a relative position with respect to the first vertex. Then when we need to translate an polygon, we just apply the translation function or translation process for the first vertex only, and rest of the other vertex will follow according to the first vertex, because those other vertices has a relation with the first vertex. So in that way we can represent the polygon also. So during the filling up process, we need to test whether any point, suppose we we want to color a polygon. Suppose the polygon is this. Suppose the polygon is this. Now we need to check. Suppose we need to fill this part. We need to fill this part. Now any point is here or here. How can we check that? Because we need not to color this point, we need not to color this pixel, but we need to color this pixel, or we need to fill up this pixel inside that polygon. So to test that, we can use this test, that is inside outside test, or we can say odd parity test. To apply this rule, we conceptually draw a line starting from particular point. Suppose particular point is this one, okay, and extending to a distance point outside the coordinate extends of the object in any direction such that no polygon vertex intersects with the line. Okay, to try to think what it is saying. It is saying that to apply this rule, we conceptually draw a line starting from a particular point, extending to a distance point outside the coordinate extents of the object in any direction such that no polygon vertex intersects with the line. So here you can see, okay, suppose this is the these two are the point. We need to check whether these 2 points are inside or outside. The point is considered to be interior if the number of intersection between the line and the polygon edge is odd. Otherwise, the point is exterior point. So here from any point, suppose this is the point, if we draw any line, from any direction, suppose from this direction also, from this direction also, from this direction also, then from this point we can extend this line to any extent as it told that here you can see no extents of the object in any direction such that no polygon vertex intersects with the line, and extending to a distance point outside the coordinate extents. So outside the coordinate. So here you can see, if we draw that same line, okay, from this point, in this way it will cut at this location and this location, and that is number is even. But in that case, if it is inside, if the point is inside, then cutting point is 1, so that is odd. So that is the odd even rule to decide whether a point is inside the polygon or outside the polygon. So here you can see, if it is, we extend that line at any direction. Suppose this is a line, this is a point, okay, if we extend it, so it will cut 1, 2 and 3, okay. So in that way we can know that whether the point is inside or outside of the polygon, okay. So we are going to develop an algorithm to know, or to how can we fill up the polygon. Suppose this is polygon, we need to fill it up. The scanline polygon filling algorithm involves the horizontal scanning of the polygon from its lowermost to its topmost vertex. From lowermost to topmost vertex means, as per the raster scan system, that this scan line will go from lowermost to topmost vertex. Identify which edges intersects the scan line. So here my main part is that we need to identify the edges and the intersection with the scan line, and finally drawing the interior horizontal lines with the specified color. So we just need to find out the intersection. Suppose this is the scan line, we just need to find out the intersection point. After finding the intersection point, we'll color this part with the required color. So in that way we color one by one, one by one, one by one, then we can fill it up whole the polygon. So that is the idea of this algorithm. So but point is that during the odd even test, if you think about, suppose this scan line, this scan line, this scan line is going through this vertex. Okay, but in that case, if you count that number of these cutting point or cross section point, 1, 2, 3, and in that case what we can calculate, 4 or 5, means 3 plus 2 or 3 plus 1, because at this point there is 2 edges but only one vertex. So that is one problem to deal with while we are trying to fill it up using scan line polygon algorithm, because to check any point is inside or outside the polygon, we need to use the odd even parity or odd even rule. So here you can see, if we think that this is an point only, then we can calculate that this is even. When it is even, then any point will be what? Suppose if we draw, suppose this is the point, if we draw that line through this vertex, okay, then how many cross section will count? 1 or 2? So that is the point I am talking about, because if we consider this is as 2 because 2 edges are there, then we need to think that this is outside, but this is not. But if we think this is one vertex only, then we can think that this is inside. So next, so dealing with the vertices, when the endpoint y coordinates of two edges are increasing, okay, suppose the y value of the upper endpoint for the current edge is decreased by 1. Here you can see, here if it is going upper or if it is going down, okay, there is two situation, is that two things can happen. When we scan the line, we are going for the next point, or at some point of time we are going for the some junction, we are going for the next point downward. Then point is, if we go downward, we'll separate the vertices, we'll separate the line, scan line, or we can say the vertices will be separated by one value. This is a scan line. So scan line is this the previous, this way we are going, this way we are going, and we'll separate the edge, or we separate the edge at that vertices, and we create a different vertex here, which is separated by one value, y minus 1. If we go in that direction also, we will separate that by minus 1. This is, see, there is two difference here. When we coming from upper, then we will decrease the outgoing vertex, but when we go from downward, we are decrease the incoming vertex. Okay, so try to remember that, because this needs to be considered during the algorithm. This difference will be created, and where to do the decreasing part. When we going upward, then we will do from this downward edge, and when we are going downward, then we will decrease this downward edge, okay, by 1 unit of y, 1 unit of y. So Now, how can we determine the edge intersection? Obviously, we will have the edge points. Okay, so we know this. Suppose we know the values of vertices and we can know the values of the slope. And in that way, suppose we plot this point first. Suppose we somehow plot this point. Next, we need to plot this point. Okay, or we need to find that cross section. So that y value or that x value can be calculated using, obviously y value is incremented by 1 because scan lines are always incremented by 1. Okay, y value, the difference of yk plus 1 minus yk plus 1 minus yk is 1, but difference of xk plus 1 and xk is xk plus 1 by m is equal to xk plus 1. Means this value can be obtained by using the previous value plus inverse of the slope. So in that way, we will try to find the x intersection point for every scan line y with the edges of the polygon. So in scanline polygon fitting algorithm, actually we try to create a data structure that is called edge table. And in that edge table, what we try to do, we try to stack the so here you can see in this stack, okay, this is YC. So this is YC is nothing but this is scan line YC. For this scan line, okay, it will contain where it is crossing. So here in this scan line, it is cross section point of edge is this one. That is why for that line, for this line, it will kept what? It contains the maximum y value. Maximum y value is for this value because that is the maximum, and it will contain also the x-intercept value. X-intercept value at the lower vertex. At the lower vertex. Okay, okay, for the edge, and the inverse slope of the edge for this edge or for this edge. This is the okay 1 by mcb. So here you can see for line YC, there is, suppose it is cross sectioning this point. Okay, here you can see for YC it is connecting through this line. Okay, so it will contain the highest value of YB, it will contain the value of XC, okay, and it will contain the slope, inverse slope of this line. Okay, here you can see YD means this line. Okay, at that point there is, for D point you can see there is 2 E and C dash. Okay, E and C dash, because we are separated this C dash, C and C dash. Okay, so for this point, for point D, there will be 2 separate part. At one part for one edge, at one part for one edge. For this part, highest value of Y is YC dash, lowest value of XD, that is XD, and slope of DC, which is should be inverse. Then YE, maximum value of Y, then XD, lower value of this, and inverse slope of DE. So in that way, in that table, for every scan line, we'll try to store the value. So this way we try to store the value for the algorithm. So suppose here you can see, suppose this is the polygon A, B, C, D, E, F, G, and we need to fill it up. So our edge is A, you can see this is 2, 7. Okay, this is 2, 7 from this point, 2, 7. B 4, 12, B 4, 12. Okay, and in that way it will fill it up. A, B, B, C, these are the edge. A, B, B, C, C, D, E, D, E, E, F, F, Z, Z, A. So in that way it will try to contain for line AB. For line AB, inverse slope is 2 by 5. You can calculate that from here. That is y2 minus y1 by x2 minus x1. So in that way, using this equation, it will try to find out the an inverse of that. That is 2 by 5. And y minimum is 7. And x is 2. And y maximum is 12. You can keep y minimum also, but you may not. That is your choice. But y max is needed, x is needed, x is 2 because this is 2, y minimum is 7, y maximum is 12, and the inverse slope is this. So in that way we will create the h table. Okay, so for this polygon we will try to create the data structure. Then here, as we have discussed, if yp, here you can see if yp less than yc less than yn, in the previous case I have discussed in previous slide, this means that yc is decreasing by 1 because we are going from this direction. We are going from this direction. That is why yp is less than yc, yc less than yn, and then in that case this yc will be decreased by 1. So new point will be, new edges will become xp, yp, xc, yc minus 1, and xc, yc to yn, xn to yn. So at that point this will become will become yp, and this will become x or y dash c. This will become y dash c. This is yp, this is yc. Okay, so that is why here you can see xp, yp, x dash c, and yp will be decremented by 1, and xc, yc, xn, yn. This is xc, yc, this is, and this is xn, yn, but this is decremented by 1. And here you can see when yp is greater than yc and then yn, then this is in this way, then this will be decreasing. Okay, this is a new line. This is previous line. P means previous, this is current, this n means new. That is why. And you can find out then interception will be different for this line, interception will be different for this line, because previously for this point interception will be counted as this one, but when you divide it, it will become different for the new line with respect to the new vertices. Okay, now what we can see is that as per our example, okay, z equal to 5, 5, a equal to 2, 7. So for a, previous vertex is z, next vertex is b. So 5 is less than 7, 7 is less than 12. So this is the case. Okay, so in that case we need to split a. Are you getting? Not local extremum. Okay, not local extremum. And here you can see for b point, current vertex, this is the previous, this is the next, and in that case yp is less than yc and yc less than yn. That is why that is also not local extremum, split B. If we can see that in previous here we can see, okay, A is not local extremum, A is not local extremum, okay, and B is not also local extremum, but C is. Now check here, B, C, D. B is previous, C is current, D is next. So here you can see the values of 12 is greater than 15, previous is greater than 15, but this is greater than 9. So this is local maximum. In that case, no need to be done about the splitting. Only if it is increasing or only if it is decreasing. Here you can see this is also, this is local minimum, nothing to be done. This is local minimum, nothing to be done. This is local minimum, nothing to be done. But in this case, this is decreasing. In this case, is increasing. Okay. So this is need to be remember out. And then, okay, as per the vertex A should be split into vertex A dash. Here vertex A should be split out vertex A dash, because we need to split this point. So one point will become 2 7 x A 2 6 and one point will become 2 7. Okay, so M is this one for this edge, okay, and the vertex A is split to so here you can see some mistakes are here. This is 2, okay, this is 2 and this is 2 7. So the next point of x dash will what, because y will be separated. Here you can see one point will become 2 7 and one point need to be calculated. Okay, this is x dash A, that is x dash A need to be calculated. So M previous values of that is 5 minus 7 5 by 2. If you calculate from this to this line, okay, so because that point will be connected with this one, okay, so that is minus 2 3. So x dash A equal to 5 into inverse of this minus into this. So it will almost become 4. Okay, so in that way we try to split the vertices. So vertex B should be split into two vertices. Here you can see B dash, here B dash, X B11 and B 4 12. Okay, M equal to 7 minus 12, M equal to 7 minus 12, 2 minus 4, 7 minus 12, 2 minus 4. Okay, in that case it will be 5 by 2. Then X dash B will be equal to 2 plus 2 by 5, 12 minus 1 minus 7, because the equation is coming from this line. Here you can see current minus 1, because this is the y value, minus p. So here 7 minus 1 minus p, 7 minus 1 minus 5. Okay, that is why 7 by 2 you can see, that is why this will also become almost 4. We need to take out the closest value of this 3.6, that is 4. So in that we will split the points. So now our edge table will be modified. Here you can see A equal to 2 7 and it's splitted up 4 11. Okay, B 4 12. Okay, C, because that is incremented and we have calculated this B, C 8 8 15, C 8 15, D 16 19, D dash, this is in 16 is decremented by 15 1, and this is 8. Okay, this is 11 5, this is 11 5, this is 8 7, this is 8 7, this is 5 5, this is 5 5, this is 4 6. Okay, because that 4 is due to this is separated out from this one, otherwise this would have been same in the previous age table. So now we need to find out the, for every edges, suppose there is edge number 0, that is edge A B dash, this is 0. For edge 0 we need to find out all the scan lines intersection point. So here we already in the edge table we need have these values. Inverse of this y mean, this x max, x and y max. Okay, so here you can apply. Already we got this point 2. For y scan line 7, for y scan line 8, it will incremented by 4, 2.4, that is almost 2, 2.4 plus 4, that is 2.8, 3. So at every time will increment by 0.4. At every time will increment by 0.4, 0.4, and this is 4. So 2.4, 2.8, 3.2, and we take the close values of 2.4, that is 2, 2.8 is 3, 3.2 is 3, and 4. So these are intersection point for this edge for every y scan line. Okay, and scan line is because 7 8 9 10 11, because this is from 7 to 11, that is a 7 8 9 10 11, and for every scan line we will measure out the intersection point. In that way we will try to find out for edge number 1 also. This is one cross section, second cross section, third cross section, fourth cross section. So in that way for every edge we'll try to find out the intersection point, because already we have the value of slope y mean, x, y max according to this table. This is modified as per the rules of this. So we need to apply this one also to create this modified edge table. Then we try to find out the intersection points, x intersection points for every y line. So in that way we create this table where we try to put for every minimum, from minimum to maximum, that is minimum is 5 and maximum is 15 for every scan line of y. For every scan line of y, to this we'll try to, this is for 5 scan line, and for 0 edge there is any cross section or not. If there it is, we'll put that. If there it is, we'll put that. So there is 4 cross section point with 5 scan line. Here you can see for 5 scan line, this is 1, this is 1 2 3 4. So in that way we can see there is 4 cross section point for scan line 5. Here you can see specifically in this point for 5 there will be this point. Okay, there will be this point. And why 4? Because that scan line will cross this point also. Here you can see for edge number 3, this is d dash, that is separate, that is we have splitted these points already. We have splitted these points, but those will that is why this point will be intersected. So and obviously E and F will be intersected, and again this Z is also intersected by edge number 5. Okay, so there will be 4 points. Like here you can see for suppose 11, suppose 11 scan line, this is 11 scan line, so it will cross section for this 0 line, because this AB is 0 line, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay, that is why suppose if you take 7, if you take 7 here, it will cross section what? It will cross section the edge 3, edge 3, 4, 5 and 6. In that way, suppose 13 we take, it will cross section the 1 and 2. If we take the value, suppose here you can see 9, 9 is cross section x intersection point is with 0 and with 0, 1 and 2. This is 2. So in that way, it try to find out the edge intersection and all the line inside that line will be colored as per our required color. So this is the scanline polygon fill algorithm. So this is one example of polygon filling algorithm, but there is another two mechanism. First one is boundary fill algorithm. So another approach to area filling is to start at a point inside a region and bend the interior outward toward the boundary. If the boundary is specified in a single color, the fill algorithm processes outward pixel by pixel until the boundary color is encountered. A boundary fill procedure accepts as input the coordinate of the interior point x, y, a fill color and a boundary color. So in this algorithm, you can see three very basic input. The point xy, which is need to be inside of that polygon, and a filling color, the color which you want to fill inside the polygon, and a boundary color which should be different than filling color. Okay, which should be different than filling color, and it will compare at every point of time whether fill color is equal to boundary color or not. Okay, so we'll go through the algorithm now. So start from the interior point. If the current pixel is not already filled, and if it is not an edge point, 2 point. Here you can see two conditions are there. If the current pixel is not already filled, and if it is not an edge point, then set the pixel with the fill color and store its neighboring pixel in the stack for processing. So neighboring pixel can be counted as 4 or 8 connected. We will discuss that here, but that thing will be stored in the stack connection of the current pixel. That means 4 connected or 8 connected pixels will be stored, and store only neighboring pixel that is not already filled up. So we need to store those points only that already not filled up and is not edge point and is not edge point. Okay, they select the next pixel from the stack and continue with step 2. So in that way we will go through that stack to fill the every points, but we need to start from any point inside the polygon. So we'll go through it again. Suppose there is two type of connection, 4 connected. So suppose this is the pixel we are currently coloring, then these 4 points will be called as 4 connected. If we talk about 8 connected, we need to talk about all the points that might be diagonal, that might be horizontal, or that might be vertical. So this is 8, this is 4. Okay, so suppose we start using 4 connected. Suppose we start from this position. Then if we colored this point, now our point is 1, 2, 3. Then we start from 3. Then for this point, this is the neighboring point, 4 connected. So for this point, 4 neighbors were this one, and this one, and this one, but this is already boundary color, so we don't need to consider this. So we need to So this is 1 2 3 is kept here in the stack, but not 4, because 4 is already the boundary color. Then this is considered as 4, but not this one, and 1 is already in the stack. So 4 is colored. Next 2 will be colored. Next to for 2 the neighbor is 5, but all other is already either in stack or either their boundary color, boundary edge or boundary points. Then 1. So now next, so here one problem you can see between 4 connected and 8 connected is that we cannot access this point when we start from this point. So that is the problem for 4 connected. That is why it is advisable to use 8 connected. But for 8 connected there is a problem like computation or storing capacity. Okay, now we'll go for 8 connected. If we start from this point, it will contain all these one in the stack. We see 1 2 3 4 5, and then for top one, this is 5, it will contain also 6, because all other points are already in the stack or might be in the boundary. Then 7 8, then this way, then 12 will be colored first, then 11 10 9 7, because all other things are colored or might be in the stack. So in that way we'll follow up and we'll color it up. So this is the way we can do filling a polygon. Next, there is another algorithm, that is flood fill algorithm. Okay, so we'll go through this. In the flood fill, starting from initial interior pixel, then fill in the contiguous span of pixel on this straight scan line. Then locate and scan . Here you can see how it is going. So this is span fill. Span fill means as per the scan line. As per the scan line, this is filling up. Suppose if we start from this starting point, for all the point, here will be colored and 2 values will be stored. This 1 and 2. Then 2 will be colored, then 3. Then 3 will be colored, then 4 and 5 and 6. Then 6 will be colored, then 7. The 7 will be colored, then 5. Then 5 will be colored, then 8, topmost. Then 4, then 9, then 10, then 11, then 12, then 1. But these are remain not colored. Next, we'll go for flood fill. So this one span fill flood fill algorithm. The next one is flood fill algorithm. Here there is a difference. Sometimes we want to fill the interior, fill in recolor an area that is not defined with a single color boundary. So problem is in boundary color or boundary fill algorithm is that we need to specify the boundary color. But sometimes what might happen is that the boundary color might not be constant. So in that case the boundary fill algorithm will not work. So that is why this flood fill algorithm will work. So here what it does, it considers that boundary color might not be same. So we paint such areas by replacing a specified interior color instead of searching for a boundary color. So here we don't search for the boundary color value. This approach is called flood fill algorithm. We just fill it up using a flood technique, but not by boundary color comparison. So this is also you can do using 4 connected, 8 connected. Okay, we start from a specified interior pixel xy and reassign all pixel values that are currently set to a given interior color with the desired fill color. If the area has more than one interior color, we can first reassign pixel values so that all interior pixels have the same color. Using either 4 connected or 8 connected approach, we can step through pixel positions. So this is the way I can show you the code of the flood fill and boundary fill. Here you can see the inputs are in boundary fill. Inputs are filling color, boundary color, and XY position of the interior point. So in that way we might go. Here you can see, if we use boundary fill to create the stack, so here you can see we are creating a recursive program by calling the same function in different direction, that is x1 x plus 1 y, x minus 1 y, x plus y plus 1 x y minus 1. It means, suppose this is the point, we are pointing this point, this point, this point, and this point. Those things are considered, and those things will be accessed using this boundary fill function, same function, recursive function. And for this also it will go for other 4, for this one it will go other 4. So in that way this is recursively it will go through. This is 4 connected because we are taking 4 direction, but if we want to take in 8 direction, this will become different. So in flood fill, here you can see the values are like x and y, the interior point, fill color, and the old color. Old color will be like previous color you have drawn. Okay. So we can first reassign pixel values so that all interior points have the same color using either 4 connected or 8 connected approach. Okay. So filling color we are comparing with the old color. So get pixel xy, we need to find out the color of the current pixel. If it is equal to old color, then we'll color the whole thing with fill color, and we'll search for the 4 connected pixels using the recursive program. Okay, and here in the boundary fill, what we are trying to find, here you can see 2 condition: current color should not be equal to boundary color and current should not be equal to fill color. But in this case we are comparing 1 point only: current color should be equal to old color. Okay, then we'll fill it up using fill color or flood fill algorithm. Okay, so this is the point about filling algorithms. So this is a big video because I need to make it in one video so that you can understand, and I think that you might have lots of doubts in this video, and also I encourage you to please go through it, and this is very important in terms of exam also. And also, as a computer graphics course, this is very primitive idea to fill something, to color something, and these are not inbuilt technique. These are algorithm that has been developed to fill the objects, to fill the polygon objects. So please go through this, and if you have any doubt, please let me know. We'll try to discuss. And though this is a very big video, but please try to go through it, and please try to go through the material given to you through Google Classroom, and through that also you can understand. But if for more understanding, you can follow this video. And also, if you don't understand something, please let me know. I'll try to resolve those things over Google Meet. Okay, thank you.